electron microscopy. We also have transmission electron microscopy over there. We have confocal microscopy, confocal laser scanning microscopy, NMR, and even XRD, single crystal. So in USIF, you will be given the demonstration of Raman spectroscopy. While in the interdisciplinary nanotechnology center, you will, although there are a number of equipments over there, but you will be given the demonstration of XRD. XRD, X-ray diffractometry, is basically used to study the crystallinity of a material, the particle size, the geometry, the phase structure. What we generally do in X-ray diffractometry is that, just I want to give you a brief information before you go and see the equipment. X-ray diffraction. Basically, light is diffracted by different planes of a material. A material has different planes present in it. When the light is incident upon it, the light is diffracted. Diffract means turn hoti hai due to the sharp edges of the material. For example, if I ask you to throw a ball on the floor, even if you do not know whether the surface, this floor is smooth or it is rough, just because of the bouncing of the ball, you will realize whether the surface is smooth or rough. Even if it is dark all around, you cannot see the floor. Just by throwing the ball on the floor and noting down the angle by which the ball is rebouncing, you can determine whether the surface is smooth or rough. The same concept is utilized by shining the X-rays on the sample, and sample has different planes. Due to the sharp planes, X-ray bend, undergo diffraction at different angles. We measure those angles and apply the equation in lambda is equal to 2d sine theta. And we measure the theta first of all and put in that equation and calculate. And lambda is also known, the wavelength of the X-ray. We can calculate the interplanar distance between the materials. If the material is very, very crystalline, as you all know that crystalline materials have very good structural arrangement. If I ask you when you enter the class, I give you enough time to sit accordingly, then this type of arrangement which I am seeing right now, it is a crystalline arrangement. The way you were standing for lunch, that was a type of amorphous arrangement where there is no regular pattern, no regular order. Similarly, depending upon the nature of the material, if the material is crystalline, the layers are properly arranged, we got sharp angles and sharp peaks. Those sharp peaks reflect that the material is crystalline, and from those sharp peaks we can also calculate the size of the crystal as well, known as crystallite size. And since we are doing this workshop, this Gyan course on nanotechnology, nanomaterials, for nanomaterials it is very important that once you prepare your material, you have to ensure and you have to prove that they are in nano range. And for that, we have to do some analysis. So we use XRD for calculating the particle size of the nanoparticle to show and to justify that what we have prepared, it is in the nano range. And through that test, along with the particle size, we also determine the structure, the morphology, the geometry. So XRD is used for that. Then we have Raman spectroscopy. This spectroscopy was developed by Sir C.V. Raman. We celebrate Science Day on his birthday. The Science Day we celebrate, it is celebrated on the birthday of C.V. Ramanji. And this technique is basically a complementary technique to FTIR. The molecules which do not show absorption in IR main criteria for a molecule to show to be active in IR, that criteria is dipole moment. Similarly, we have polarizability for Raman. If a molecule does not have a dipole moment, it is inactive in IR, but in that case we can use Raman spectroscopy. So both IR and Raman are complementary. Both of these techniques are based on rotational as well as vibrational transitions. So the energy required for these types of transition are a little bit less as compared to UV. UV is called as electronic spectroscopy because it involves electronic transition. For electronic transition, we need large amount of energy, and therefore we use UV radiations which have shorter wavelength and higher energy. But for IR, we utilizes IR radiation. In case of Raman, the detector, in any of the spectroscopic technique, the two main components, the two main units of that spectroscopy equipment are the detector as well as the light source. So for Raman, we use laser, the light amplification for stimulated emission of radiation. That laser light is used as a light source, and charge coupled devices are used as detector. So these are the two main components of Raman spectrophotometer. On the other hand, we use X-rays. X-rays are generated when beta particles are being targeted on a soft material, then X-rays are emitted. Those X-rays are then fall upon the sample, they are diffracted, and we'll get the angles of diffraction. From there we get information relating to that. So these are the two basic techniques which we are going to see today. Demonstration will be given. The bus is standing outside. I think I have already covered. No point of showing the same which I have already covered. We are already late also. We have given 2 o'clock time to both those centers that will be there by 2 o'clock. So we'll be leaving right now. Clear? 1 to 30, group 1, along with you, with the camera. 31 to 68 in group 2. Please proceed. Dr. Farasha has already left for nanotechnology.
To the Interdisciplinary Nanotechnology Center as well as the University Sophisticated Instrumentation Facility. And we have been very fortunate that the team of USIF and INC, they have explained the instrumentation. They have arranged our visit, followed by the demonstration of some advanced scientific instruments, especially the XRD, X-ray diffractometry, the Raman spectroscopy, scanning electron microscopy, and transmission electron microscopy. And yes, of course, XRD single crystal was also there. I thank the whole team of USIF and INC. It was very useful and enlightening experience for the students of the GAN program. Although most of the time scholars are a bit aware of these techniques, research scholars are using these techniques, but most of the times PG and especially the UG students have not even seen those advanced equipments. So it was a very good opportunity for the students to see the machines, to understand the working principle and how the sample is being studied, the experimentation has been done. This has been explained in a very detailed manner. I have collected feedback from the students, and even I was also present physically in both the centers, INC and USIF, and everything went very well. The participants enjoyed a lot, they learned a lot. Although it was planned that before moving on to those centers, we'll give you a brief information about those techniques, but due to our engagements, we could not give you the presentation through these PowerPoint slides. I just give you a brief idea yesterday without using the PPT. So today since we have time also, I have been explaining you these two techniques. The Raman spectroscopy. The Raman spectroscopy. Raman spectroscopy, as I said, it is a complementary technique which completes the IR technique, especially those molecules which do not have a permanent dipole moment and which are IR inactive. They can be studied via Raman spectroscopy. The best thing about this technique is that it has been developed by our own scientists, Sir C.V. Ramanji, and he discovered this phenomena of Raman scattering on February 28, 1928, for which he got Nobel Prize in 1930. And since then, the government of India has decided to celebrate that day when Sir C.V. Raman has discovered this phenomena, and therefore we celebrate it as National Science Day on every 20th February. All the research institutions, universities, colleges, various departments of AMU, we celebrate this day by having some lectures, some talk on Sir C.V. Raman, his research, his life, and how important is for us to be more of scientific temper, how important it is to nurture scientific temper in our student. As I said, it complements IR, it is quite related to IR, so it is also based on vibrational as well as rotational motions. Just like we have UV, which is an electronic transition spectroscopy, also known as electronic spectroscopy, and since electronic transition requires the highest amount of energy, so we need energy of UV region, which ranges from 150 to 190, it is called as the vacuum ultraviolet region, then from 190 to 360 or 380 UV region, then from 380 to 760 we have visible region. But for vibrational and rotational transitions, the energy required is not very high, so we can have it with IR radiations, which have a little bit less lower energy when compared to UV and visible. The principle of Raman spectroscopy. When light falls on matter, when light interact with a sample, this interaction either it may be elastic or it may be inelastic. When the interaction is elastic, nothing will change. The energy wavelength of the light that falls on the sample, because it is an elastic interaction, the same amount of energy is being carried by the scattered light. Since there has been no change, it is of no use. While in case of Raman scattering, that in elastic scattering is called as Rayleigh scattering. Now we have some inelastic scattering as well, which is called as Raman scattering. And whenever this inelastic scattering occurs, there are again two possibilities. In one of the possibility, the light scattered is having lower energy than the incident light, which means that some of the amount of energy which is being carried out, which is being carried by the incident radiation has been absorbed, resulting into the excitation of the molecule, while the resulting energy is being scattered. On the other hand, there is another possibility that the scattered light has more energy. This condition may occur whenever the molecule is in excited state. It comes back, it releases some energy along with the energy of incident radiation. So when it gets energy of the deactivation of the molecule as well, so that energy becomes even more than the energy of incident radiation. In the former case, we have Stokes shift or Stokes lines, while in the latter case we have anti-Stokes lines. So as this slide is showing, in case of Rayleigh scattering, the photons of the light which is falling on the sample, they do not get any energy, they do not even lose any energy, because it is a type of elastic collision. All the energy is conserved. However, on the other hand, when it is an infraction, in inelastic collision, in elastic scattering, the incident photon may lose some energy or gain some energy. When it loses energy, the energy of the scattered line is lower. It is called as Stokes lines. On the other hand, we call it as anti-Stokes line. And in any of the spectroscopic technique, or I should say in all the spectroscopic technique, there are certain few components which are integral part of that machine, which must play some important role, without which it is not possible to complete the study. Out of those components, the two major components are the light source and what is the next? The detector. Although we have monochromator in all those spectroscopic technique, and a monochromator consists of, what does monochromator consist of? Slits and something to break light. It may either be a grating or a prism. So for a monochromator, we need either a grating or a prism which breaks the light into individual colors, and then we have entrance and exit slit to select a particular wavelength of light while deselecting the others. So that monochromator is of course used, but the main components are the light source and the detector. In case of Raman, we use laser light as a source, the light amplification for stimulated emission of radiations, while the detector which is used is the charge coupled devices which collects the photons falling on it and convert the intensity of the photons into an electrical signal. So Stokes lines or Stokes scattering means the scattered photon has somewhat lesser energy than the incident photon, and it will happen when the photon of the incident light transfers its energy to the molecule, resulting into the excitation of the molecule. When molecules undergo excitation, it absorbs energy from the incident radiation, resulting into the loss of energy of the scattered photon. While on the other hand, in case of anti-Stokes scattering, the molecule may already be in excited state. The molecule deactivates, releases energy. That energy is being taken up by the photons, and the scattered photons have higher amount of energy than the incident photons. So the Raman spectrum, these you can see, if you see the middle, this excitation and relaxation, here you can see the distance, the energy levels are same. This shows Rayleigh scattering, which is an elastic, which is a elastic scattering, no change in the energy of the photon. While in case of the other two, at the corners, we have both sides Raman scattering. One is the Stokes line, other is the anti-Stokes line, and you can see the distance when it is going up, when it is being absorbed is high. So energy absorption is high, more energy is being absorbed by the photon, the incident photon, while the scattered photon has lesser energy. While in case of anti-Stokes line, it is the opposite. When it is released, when it is scattered, it has more energy than the incident photon. The same has been explained over here. I think if you remember Professor Hatau's lecture on day 1, while he was talking of graphenes, he showed you various spectra of Raman, and there he shows that Raman spectroscopy is one of the best technique to characterize graphenes. It helps you to study the disorderness or the defect density of graphenes. Just by measuring the height of D and G bands of Raman spectrum, we can identify the defect density or the disorderness of graphene. So, by looking on the Raman spectrum, you may identify whether your graphene sheets have defects or not, and if there are defects are there, what is the density of those defects. So, it is one of the very good technique for graphenes. So, there is a term called as Raman shift. The Raman shift is basically calculated or by just measuring the frequency difference between the incident light and the scattered light. That frequency difference is basically called as the Raman shift. That frequency can be converted into energy by E is equal to h nu equation. This Raman shift is given in the form of wave numbers, just like we have in IR. In IR also you must have seen the IR spectra, where we have intensity on y-axis and on x-axis we have wave numbers. Can anybody tell me the light source of IR? Which light source is used just to make it more interactive? Anyone? Any guesses? Other than teachers? Is tungsten? No, 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 no. It's a nurse glower which has oxides of certain metals. When it is heated at high temperature, it starts emit IR radiations. And do you know that IR radiations are very useful in night view cameras as well? Because IR radiations have thermal energy as well, they carry thermal energy. And those night vision cameras are nothing but they are based on IR radiation. A body which is hot is being shown red or orange color, while colder bodies are shown in light colors, blue color. Have you heard about a telescope called as JWST? James Webb Telescope? I must have sometimes explained it in class. It was launched few years back, and much before that another telescope was launched which is called as Hubble telescope. And you might have seen on the internet that the images of Hubble telescope are good, but they are a bit blurry, especially if we have a cloud in between. For example, there is a galaxy, we have a cloud of dust or even some gases present, so the images are blurry. But when you see the image of JWST, the James Webb telescope, by the same of the same region, you will get very clear images of those galaxies with no blurring, with no effect of the dust particles. Why? Because the basic difference is that Hubble telescope captures visible radiations, while JWST captures IR radiations. And IR radiations are even better to carry out, to take informations with them. They can cross through the clouds of dust and gases and gives you a very clear image. All radiations with higher wavelengths are very useful for carrying information, for transferring information. And therefore we use, for radio communications also, we use radiations which have very high wavelength. So even telescope which is based on a radiation that comes in IR region, because of higher wavelength, they provides even better images. Anyway, coming back to Raman shift. So Raman shift, in the Raman shift is basically defined as the difference in the frequency of the two incident as well as the scattered lines, and then we plot this Raman shift on one axis and then we have intensity on the other. Of course, the shift is, although it depends upon the nature of compound, of course, it is independent on the source or the excitation source frequency, because we are calculating the difference. We are not taking the absolute value. The absolute value depends, but the difference always independent of the initial excitation source frequency. As we have In case of IR, we can identify the symmetric as well as asymmetric stretching. Symmetric stretching when the atoms they are moving in the same direction, and for asymmetric opposite, and bending we have different types of combination which is called as rocking, scissoring, wagging and twisting. Raman, as I said earlier, it is even useful for compounds which you do not have dipole moment, especially the diatomic molecules, for example N2 and O2, since they have two oxygen atom or two nitrogen atoms having same electronegativity, so the dipole moment is 0. In such a case, IR is not useful, these compounds are inactive, so we always prefer Raman spectroscopy. It can also be used for symmetric CO2 because symmetrical CO2 is inactive over there and it can be studied via Raman spectroscopy. Similarly, benzene and CCl4 also we have the same condition, and therefore Raman active bands are there and we can identify, we can characterize, we can study CCl4 as well as benzene by using Raman spectroscopy. These are the this is the image of a Raman spectrometer. Again we are using laser source, laser light, monochromatic light with wavelengths 532 nanometers, 633 and 785. Visible range. The detector against charge coupled devices or photodiode arrays. Photodiode arrays also they collect the photons, they convert it into electrical signal. Then we have filters which behaves like a monochromator. This is just a working principle where we from the source the light is coming, we filter it, pass through the entrance slit. This lens is just to turn it. Grating is basically used to break the light into individual pieces, into individual colors. It breaks the light into individual colors, and then finally it passes on the detector. Here it is passed through the sample and finally it enters, and grating helps to break it into, and it finally falls on the CCD detector or PDA detector, the photodiode array detector. What is the importance or the advantages of Raman? It is a non-destructive technique. Sample remains good. Can be used for aqueous environment because most of the techniques you cannot use aqueous media directly. If you have a sample in aqueous media, you have to extract it into an organic layer, then only you can use. So the beauty is that it reduces the tedious protocol of extraction. You can directly use the samples in aqueous media. So the sample preparation is quite easy, very useful for organic molecules, inorganics, even biological materials, and quite specific also. Specificity helps you to identify some selective compounds. The resolution of the machine is also good. You can have two peaks quite resolved in a better way. Here it is mentioned the key points, especially for graphenes. In case of graphene oxide, once again I am telling you, from graphite when we exfoliate, what we get is graphene oxide, which is having lower conductivity because of the presence of COH, OH groups. In order to get graphene, we have to reduce it. The process of reduction does not remove all the oxygens. Therefore, after the reduction, we do not call it as graphene, we call it as reduced graphene oxide. So for that graphene oxide, before the reduction, the D and G bands are at 1350 and 580. These are the position on x-axis, means you get D bands first, followed by G bands, and depending upon the height, the intensity of D and G bands, just by
taking the ratio intensity of D bands divided by intensity of G bands. Higher this value means higher the disorderness. If the height of D peaks is very high, this shows higher level of disorderness. The same is intensity ID is intensity of D bands and IG is intensity of G bands. These are the structures. This is graphene, no oxygen. When we exfoliate the graphite, we do not get graphene, but we get graphene oxide. If you do the Raman spectroscopy, you can clearly observe and prove if you have graphene, you will get a sharp peak, only G band, no D bands. But since what the method which we are using, we are producing graphene oxide, so we get two peaks, that also not very sharp, the D and G bands. When we reduce it, the reduced graphene oxide has some sharpness, the peaks are even better from graphene oxide. So, from the intensity and the ratio we can identify the disorderness. Conclusion, it is a powerful technique, complement the IR spectroscopy used for compounds which are inactive in IR, especially useful for diatomic molecules or symmetrical triatomic molecules. The role is growing in interdisciplinary areas, in material sciences, biotechnology, DNA. Since it is a non-destructive technique or non-invasive technique, we can use for life systems, in vivo studies as well. Now XRD, the X-ray diffractometry. I told you that here in this technique, X-rays falls on a sample, and just like when they fall, they get diffracted. Depending upon the surface and the planes of the molecule or the solid and the structural arrangement, these X-rays are diffracted at different angles. I gave you an example of a rubber ball. If you throw it on the floor and the floor is rough, it may go anywhere. But if the floor is smooth, it may turn at a sharp angle. And if you throw it 10 times, if the floor is smooth, this angle will be same. But if it is rough, sometimes it may go to that side, sometimes it may go to the other side, or even straight. The same concept, if X-rays when fall on the sample on the solid, if the solid has perfect arrangement of atoms, they are being diffracted at sharp angles. If the arrangement is not perfect, if the arrangement is not long range, if it is not a good crystalline material, it has amorphous arrangement with no regular order, it may diffract it to anywhere, to broad angles. So then the machine measures those angles. They basically, the diffracted X-rays are being captured. The intensity is red. The angle of diffraction is red by applying the equation, and lambda is equal to 2d sine theta, where lambda is the wavelength of X-ray radiations. D is the interplanar distance between the different planes. Theta is the angle of diffraction. So the machine measures and gives you the theta value. From that theta and this equation, you will be able to determine the interplanar distance. Also from this theta value and the sharpness of the peak and the peak position, you will identify whether the sample is crystalline or not. And on the basis of those peaks, you will be able to determine the particle size, or I should better say the crystallite size of the material, by using a very famous Debye-Scherrer formula. By applying the Debye-Scherrer formula, you can determine the particle size. So X-ray diffraction, it's a versatile technique, again non-destructive. To study the geometry, the phases, the crystallinity of the sample, how the atoms are arranged, the interplanar distance, as well as the particle size. XRD depends on, or it relies on, the scattering of X-rays. When they fall on the solid, they are being diffracted in different directions. And when you have visited yesterday, you have been given the demonstration of two types of X-rays. One was PXRD, powder X-ray, which is very useful for nanotechnologists, the material science. The other is called a single crystal X-ray. The difference is that when we are doing PXRD, we use sample in powder form and we put a powdered sample. All these dimensions, all the phases are exposed towards the X-rays, because some particles may have X phase in the at the front, while some other particles may have Y phase, Z phase, because when you are putting powders, there are number of particles. So because of the presence of number of particles, all the phases, angles, all attributes are being exposed. But when we are dealing with a single crystal, there is a provision in the single crystal machine that we have to rotate the sample in all directions, so that all the phases, all the edges, all the angles should be one by one exposed to the X-rays. If we are not rotating, we will get the data from one side of the sample only. So for single crystal, we have to create a crystal first and then we rotate it to expose all the uh, these phases and angles and edges to the X-rays. And then we use the Bragg's equation, which I have just mentioned, and lambda is equal to 2d sine theta. So when a monochromatic light of X-ray interacts with a crystalline material, note it down, the crystalline material, the atoms, they act as an scattering center and they scatter the light with some sharp angles. And from there, those angles we can identify and draw a diffraction pattern, draw the structure, the morphology of the sample. This is a solid. You have been shown here the different planes. When the X-ray falls on the front, the first layer plane, they are diffracted in one direction. Since the distance is constant in all the planes, the sample is crystalline. Again you can see the angles are same and they are being diffracted at sharp angles, same angles. By measuring the sample, by measuring the angle, and based on the lambda and n values, we can determine the D. Again, the instrumentation in all spectroscopy, the two most important are X-rays and detectors. We also have sample storage and goniometer here. This is the X-ray tube and a goniometer which helps us to rotate the sample, and from this tube X-rays are being generated. Here we put the sample. On one side we have a connection for incident radiation, on the other side we have detector. When X-rays falls on this object, on the sample over here, they are being diffracted. Some are going straight transmitted, by some of them are being diffracted. These diffracted X-rays are captured by the detector and the angle as well as the intensity is calculated. And you can see that the angle, the sample is a little bit tilted because of this goniometer. We are rotating, we are exposing all the dimensions, all the faces. So X-ray tube, the sample, this is scattering, and again we have a detector. This is the schematic diagram. This is the this is also even a schematic diagram. This is a flow chart. You can see how the different parts are connected. For the machine which we are using and which you have been given demonstration, the lambda is 1.54. We use copper K alpha radiations with a wavelength of 1.54 angstrom. The goniometer, as I said, it is used to precisely control the angle of the sample and the detector. We can rotate it, we can change the angle, we can change the platform, We can tilt it, keep it straight, just to expose all the dimensions. We can make measurement of theta or 2 theta. So, the main purpose of goniometer is for the sample alignment and rotation. Then we have detectors. There are different types of detectors possible. Scintillation detectors. We generally use solid state detectors here to check the intensity as well as the angle. These are some samples which are being prepared for the analysis. There is a sample holder, we put the sample over there and do the analysis. And this type of curve is obtained, this type of plot is obtained. You can see very sharp peaks. This shows the crystalline behavior, and from these peaks you can also identify the crystallite size using Debye-Scherrer formula. If these peaks are broad, this shows the material has low crystallinity. I think I am running out of time. These are the application used for studying the morphology, the crystallinity, the particle size, even orientation studies also. If you have any question relating to XRD or Raman, I will try to answer, and then Dr. Asfar will be explaining you little bit about Raman spectroscopy, the application part, just for 5 to 10 minutes. Then we will proceed for lunch. Thank you very much. कुछ लगाना है? ठीक है, घंटा खींच के आराम से.
Results, and this is our paper, research paper of my PhD work. So basically the application which we done in this paper is the removal of uranium ion, uranial ion. This is the actually our supervisor has some research project related to the radioactive material removal of bark. So we use graphene oxide, reduced graphene oxide as an adsorbent. So what we want to share here is some results. So first of all, I want to show some tentative scheme. What we discuss in this paper is that this is a graphene oxide, as you see here, and we use some linkers and nucleotide AMP, and this is a DCC, dicyclohexyl amidamide, and this basically the linker which convert the carboxylic acid into the amide group. So we fabricate our graphene oxide with this AMP using DCC as ethyl glycol as a linker. So we got RGO AMP. This is RGO means reduced graphene oxide, AMP because we use AMP. So we give the name AMP. So now come to the results, which is very important to understand. So this is not a slide, this is actually paper we directly discuss here. So first of all, come to the FTIR plot, FTIR data. So the red one is the graphene oxide. So this in graphene oxide you say is a 730. So this 730 is the signature peak of which functional group? It is a signature peak of carboxylic acid, near about COH. This is a peak of C double bond O, the COH of the carbonyl group of the COH. And this peak around 3440, this represents the signature peak of hydroxyl group of COH. When we convert it into RGOMP, when we reduce this, so what happened? We observed different types of extra peaks around 3328. Can anyone tell this 3328 peak represents the NH peak, the stretching peak of NH, because we convert the carboxylic acid into amide. So we have NH peak. This 2933 and 2840 is basically the peaks of the CH peaks, strong CH peaks. And this 627 is basically the carbonyl group peak of the amide, 627. And you feel that this 1730 peak is disappear in this RGOMP. It means that our carboxylic group is mostly converted into the amide group. And we also confirmed this experiment by using a specific titration called Bohm titration. Bohm titration. Many of you, I think, listen this first time, Bohm titration. This is a titration in which we can calculate or we can quantify the concentration of the acidic functional group which is present on the graphene. So it is not a time to define this. So this 1627 is the peak of the amide group, and this 1575 is the peak also related to the peak of the amide. And this 1230 peak is of the phosphate group, because AMP is a nucleotide, it has a amide group also and also phosphate group. So this represents, so from this we can conclude that we have a very good fabrication. We can reduce the R graphene oxide into RGOMP. Now come to this one. So this is a Raman spectra of the GO and RGO. Now you can, people, I think you can easily interpret this. You can see that in case of GO, the ID by IG ratio is 0.859, and in case of RGOMP, the ID by IG ratio is must be increased or must be reduced? Must be increased. And what we get in the result? 0.880, because when we reduce our graphene oxide by AMP, so what is the meaning of this? We increase the D band. We develop the defects in the RGOMP in the basal planes, so that the intensity of D get increased. We increase the wettability, as Professor Leo discussed in the very previous lecture of this GAN program, the wettability. So it enhances the wettability. So we get ID by IG ratio in case of RGOMP get enhanced. So when we reduce it into the, so we can make our RGOMP a very good adsorbent. Now some results I want to show you, not all, but a comparative table I want to show. This is the XPS result, very normal, nothing like very new in this. But I want to show a comparative table of this. What is the beauty of this RGOMP? Look this. Look this. This is a comparative table. What we do in RGOMP in last 23 CL number, the RGOMP, we get the Qmax value, which is the adsorption capacity, mg per gram, is 3024. Means 1 gram of RGOMP adsorb 3024 mg of uranyl, and uranyl UO2 2+ is itself a big molecule, but it enhances the surface capacity. So we get this result of adsorption capacity of 3024 in a very quick time of only 4 minutes. So you can see, you can check or you can absorb the surface activity of the graphene. In just 4 minutes you can get the very high adsorption capacity of 3024. So from this, what we can say that if we functionalize our graphene into another functional group, by using another functional group, we can use our graphene oxide in different applications. As for example, this is the one example in which we use uranium. People can use this in other heavy metals like arsenic, lead. So those you people, if you want to work on this application part of the graphene in the research, so you can work on this, because there is a very scope. Nowadays, for example, in India, when I was in some lab, there is a very big problem of arsenic in UP East, mainly in UP East. So we have to think like this, we have to approach like this our research, so that we can prepare some type of absorbent like this, which is cost effective also, which is very good reusability, we can use good recyclability. And one more result I want to share also this, our material has very good recyclability also. We can use this up to 5 cycles and we can get the adsorption capacity. This is the theoretical, it is experimental adsorption capacity around, I think this one is around 150. So we can lose only around 30 to 40 absorption capacity, 30 to 40% of this, and we can get up to 5 cycles. So so what I want to say that if you want to work in this material chemistry, so you have to prepare that type of absorbents, that type of the material which has good recyclability, or most thing is that most is thing you have to prepare more economical also. How you make economical? You enhance, you increase its recyclability so that you can use up to 10 cycles, up to 15 cycles and commercialize it. And main thing is the commercialization. So this up to the results which we want to discuss here, because application part is very important. How we use the graphene in the water treatment. So anyone have any question related to this? Because it take already we are 5 to 7 minutes over. Very quick. Quarter past. Anyone? This is the actually this is the basically the tentative scheme which we prepared by after characterization. What we think, because we not perform any DFT studies in this, so that we can confirm this. But what we think and what we get from our FTIR data and from Raman and from XPS, that basically what AMP and DCC, AMP is basically the nucleotide and DCC is basically the linker, which convert the carboxylic acid into the amide. It is a very good linker. You just put the DCC in the sample in a millimoles, you calculate the millimoles and put into the into the round bottom flask and put go for 12-hour reaction. You get a very good results. So this is basically, and this structure you can easily differentiate from the characterization part. For example, you can easily confirm from the FTIR, and you can also, we also perform the zeta potential. The zeta potential of, you can see the red one is graphene oxide. You see that when we perform our zeta potential from 2 to 9, so you can observe that although pH 2 is very acidic, it means very high concentration H plus, but in that case, in that pH also, our graphene shows negative zeta potential. But when we same apply for the reduced graphene oxide, we can get the zeta potential in positive part. It means that we have some functional group which can acidify, which can easily acidify at this quotient. Therefore, we get the 0 point charge at 2.31. When we cross this pH, we get the negative values. This is also the difference which we observed after the modification. Experimental point of view. Actually, we confirm, we take this, we observe this, that the COH group which is present at the outside the basal planes of the graphene oxide. Actually, we show, this is, read this, representing the, it is a tentative sites. It is a tentative sites. You confirm it from some theoretical studies like DFT, I think. Anyone? Functional group के लिए डाटा it is fixed. It is fixed. Linker मतलब जो link कर दे, which link two functional groups, है ना? Anyone? I already told you that we go up to 5 cycles. We go up to 5 cycles. So you can optimize more. It is up to your hand how you produce your material. Very good question, because uranium has a tendency, for example, some elements have a tendency to bind particular another elements. For example, if you found iron, if there is, for example, in geological terms, if we have iron, so it is very probable that you found arsenic here, because arsenic has a very strong bonding with iron. Similar in these cats, uranium has a very strong bonding with phosphates and nitrogen. Therefore, sometimes you found some studies that where there is phosphate rocks are found, you get uranium also. When you check some studies in Haridwar side, because there is a Ganga, so in that there is a very rich phosphate rocks. So in some studies, it confirmed that we found uranium in the, because uranium leach out the system and comes into the groundwater. So therefore, we use this concept and modify our material by using phosphate groups on the one side and nitrogen on the first, because nitrogen has also very good compatibility with the uranium. So we have two binding sites, one for the nitrogen, one is the phosphate. In that, uranium becomes in the middle, so uranium binds with those, with phosphate also and with the nitrogen. Therefore, we get very high absorption capacity. With one molecule, you have to calculate with this, with the millimole formula. What, this is nucleotide, you can easily purchase from the market. It is an available compound. बिल्कुल कर सकते हैं, बिल्कुल कर सकते हैं. आप कोई भी सिंपल फॉस्फेट ग्रुप ले लीजिए. आप फॉर नाइट्रोजन सोर्स यू कैन यूज एमिनो एसिड्स आल्सो. ठीक. Now it's time for lunch and we can meet on 2 o'clock. At 2 o'clock sharp, please come and assemble here in the conference.